So another day and another stream. And yeah, looks like I switched out my microphone setup and now have a new microphone. I hope that goes well. If there's any audio issues, please do let me know, because I think I've received quite a few complaints about that. Anyway, so today I wanted to talk about GPU drivers, and specifically let's just look at the Nova GPU driver, which is an open source driver that Nvidia is building out. So basically they're adding this to the Linux kernel, and that's what's really interesting, is that it's written in Rust. And so at the outset, my interest over here is that I'm pretty much a Linux kernel noob. I have no knowledge of the Linux kernel as such. I've always wondered how it would work, etc. And this looked like a great segue to try and get to know A, the kernel, and B, also how would one go about writing a GPU driver? What sort of goes into it? Because if you think about it, pretty much any framework, say CUDA, say Vulkan, say PyTorch, or the previous one that I talked about, which is Burn, the framework, pretty much any framework that you touch, ultimately it will have to talk to the driver, right? So you can think of all these frameworks as sort of abstractions that are layered on top of the driver. You're going to be talking to the driver to get the GPU to do the work that you want it to do, right? So all the registers and all the memory and all the synchronization and all the mailboxes and all of that stuff that actually goes into programming the GPU, that's what the driver handles. And the Nvidia driver specifically is a little different, because you remember I talked about this particular scene where, let me see if I can find it. What was that? Yeah, this one. Yeah. So yeah. So if you see this, if you remember, one of those old streams I talked about this, where I said basically the GPU is the high level overview of how you would think about programming the GPU is you send it commands and then it responds. Now those commands can get really complicated really quickly. Primarily speaking, let me see if I can find a simpler thing. Yeah. This is one of the other pictures I talked about. This is again from AMD's HIP thing, where the host is going to be crafting these commands, and then it's going to be submitting those commands to a queue, which happens to be a ring buffer and all that great. But ultimately, once you submit those commands, there's something called a command processor. Now, this is nothing but an actual CPU that is embedded inside the GPU, right? So this is different from the host processor. This is a command processor where the job is to accept incoming commands, then sort of pull them off the queue and decode them, and then basically dispatch them as such. And that's sort of what you're seeing over here. You'll have different kinds of commands over here, like a memory copy command and an actual kernel launch. This is where the work gets done. And in AMD's case, you'll have something called an asynchronous compute engine that sort of schedules that onto the compute engine as such. So all that is something that we've seen. In our case, when I'm talking about the driver, we're specifically talking about all this stuff. Who does this kind of work? It's the driver. And when you think about CUDA or Vulkan or any of them, when we say we're recording commands into a command buffer, at some level of abstraction, what we're trying to do is, we're trying to stick to the programming model that the GPU ultimately uses underneath everything. And that's why, all these, frameworks, etc., are sort of high level. Vulkan is not. Vulkan is just a pretty low level thing. And I think that's also its Achilles heel, because it can get really complicated for no damn reason, right? Anyway, so that's the point of a GPU driver. Ultimately, everything that you want to be able to do with the GPU is going to be driven by the driver, right? That's what a driver is. Any piece of hardware that exists out there usually has a driver. That's the software interface with that piece of hardware. And for GPUs, no different. It's a piece of hardware. You'd want to control, you want to sort of work with it. You'd need a driver. And the interesting thing is, this is A, open source. This is B, written in Rust. And it got me thinking, if I'm pretty much invested in trying to understand all these different frameworks, not at the highest level abstraction, but the lowest level abstractions, it makes sense to actually look at this. How is a driver built? What goes into making a driver? There's a bunch of pieces, obviously. I've also touched upon that, but not in a lot of detail. And this looked like a perfect way for me to get into Linux and also understand how drivers are built, specifically GPU drivers. So without sort of spending too much time on context setting, let's just jump into this. So there's this thing called the Linux kernel. So, and if we actually go ahead and look at it, the kernels, I think the repository layout is really nice. It's pretty simple, except when you start working it gets really complicated. Because primarily I think of the build system. I'm still wondering why the build system is just still make and not something better. Anyway, so what I wanted to do was jump into the Linux kernel, specifically look at the Nova driver, understand the pieces, and also in that process, I think there's quite a few talks that were given by a number of people working on adding Rust support in Linux. And I also wanted to look at, how far that's come along. So it's pretty far. That's one. And second, how much of that is directly being utilized by these new drivers that are, making their way into the kernel. So let's look at that. The first thing is you'll find a separate folder for Rust. All things Rust live in here in the kernel. You'll have, the kernel stuff. That means if you're going to be working with the kernel, then the Rust for Linux project already provides you with some primitives and some interesting things that you can make use of. So you're going to have to maybe do them yourself or something like that, I guess. Yeah, that's pretty much it. So the main folders are the kernel, the pin initialization. That's kind of interesting. I think they went to town with the idea of Rust macros. I'm pretty sure they love it, because I was just looking at the amount of effort that's been put into pin initialization, the API. It's very, very interesting. And then we look at something like drivers, and in here, what we do is we simply, where the hell is that? GPUs, and then we go look. There's actually pretty few of them over here. I don't know why. I don't know if drivers are maintained somewhere else as well. I don't know. I just know that Novacore is in the upstream, and there's, by the way, we're not going to get into the depths of everything because the driver itself over here is minimal. There's not much that's been added. It's basically bootstrapping the core pieces of the driver. There's nothing else happening over here. But even that is sort of interesting if you just want to learn how how do these things work. And this is the best time as well because it's not too complicated already. And so let's look at that. So the first thing is you'll find Nova Core. Nova Core is, so the way the Nova driver is actually written in Rust is it's a two-tiered implementation is what I'm calling it. Let me just pull up my notes over here. So basically there's two parts. One is the Nova Core part. This is what directly interfaces with the GPU. So it's got things like the driver, the GPU abstraction, the driver abstraction, the registers that you can work with, and then there's something called the firmware, which is, I'll get to that part. That's the first piece. And then there's the other piece, which is what is being called DRM, which I believe stands for Direct Rendering Manager. And this is what the user space people deal with. What do I mean by user space? I'll get to that. Let me just pull this up. Yep. So you have the user space component. No, not the user space. This is still part of the kernel. What I mean to say was user space applications like, let's say, Vulkan or whatever, they will pretty much call into this, the DRM piece. And then the DRM piece is going to go ahead and sort of communicate with the actual underlying Nova Core driver using what's called an auxiliary bus. And then the Nova Core driver will use the traditional PCI bus, which is what we use to connect GPUs to a system. That is sort of the picture. So instead of me talking about this, let me just show you what that looks like. So here's what that looks like. So you've got user space applications. These can be things like OpenGL, Vulkan, CUDA, whatever. Via DRM ioctls. I really need to understand ioctls a little more. So I'm not going to touch upon that right now, but that's the interface basically between user space applications and the kernel Nova DRM driver, where we do things like device management, buffer object management, and the user API that's sort of exposed. All that's going to be happening in the Nova DRM driver. And then there's an auxiliary bus for the DRM driver to talk to the Nova Core driver. Here is where you'd see the PCI piece comes in. So things like, not scanning the bus, things like actually working, managing the device over PCI is sort of done over here. There's some level of hardware register access that you have. And then you do something called firmware loading, which I'm going to get to. And then a little bit of GPU initialization is also sort of baked in here is what I understand. Right? So there's like two buses and a two-tiered structure. That's sort of the mental model for this particular driver. It may not necessarily be the case for all of this. Having said that, one of the things that I've been wondering is, why hasn't anyone written, or it's very, very difficult for me to, I haven't even seen a single GPU driver that's bare metal. Everything's attached to some OS. Not sure why. Why can't you just write a driver? A bare metal driver. Obviously, you're going to need some, some what you'd say infrastructure, like a minimal runtime that you probably need, like something to do with allocation, memory allocation, and other things. But those are all very small things. At least from what I've read, I think that is possible. I just don't know why they don't exist. Anyway, so that's the mental model. That's kind of what this looks like. And I've been just mucking around, digging through. So there's no tests that I can do right now because I don't have an Nvidia GPU, and I've been trying to look on the cloud, say, okay, let me just run a Linux VM and I want a GPU attached, and I was not able to find one so that I can show you what I've learned. But we can just read the code, so let's just do that. All right, so as I said, Nova Core, this is the low-level driver or abstraction layer, as I've called it over here. And it starts off with, where did I go now? Right, so let me close DRM. Yep. It starts off with this over here. So some of the things that I learned along the way was, one is how easy is it to work with Rust in the kernel? Turns out it just takes a little while, but you have to get your head over make, the build system that the kernel uses. You make this, you make that, you make this, you make that. Oh my God. And it's really, I'm pretty sure the people who've sort of been working with are very happy with it, but I don't think you're going to attract a lot of new folks if you're going to continue to use the same old build system. This stuff can be, I mean, it can be better, is all I'm saying. So the other thing is, one is when you just clone the Linux kernel repo, you go ahead and basically say make Rust first, and you need to check whether you have Rust available. And there's a bunch of targets that are available in the make file. You can sort of go through all of that and set it up. It's not a lot of work, but I think it is some work. And then the one thing that I would certainly say is definitely get Rust Analyzer working. And there's a target for it. It's just make Rust Analyzer. But before you do that, you need to install Rust, and don't install it via the standard distribution packages, etc. You'll need some nightly features that maybe are not available, all that stuff. But apart from that, you'll need to ensure that you can go ahead and get Rust Analyzer working. And you may be wondering, how is Rust Analyzer working for this? There's no cargo.toml file, etc. over here. True, for non-cargo projects, Rust provides a different way. There's something called the project.json file method, which is, let me pull that up. Is that, yeah. So this is pretty much a different way of doing things, wherein you can go ahead and basically generate this particular file, which is going to go ahead and create a record of all the different crates that are in use, all the different dependencies those crates have, a whole bunch of things. And then you can supply this file to Rust Analyzer, right? Rust Analyzer, once it has this file, it should be able to provide you with everything that you're used to. The syntax highlighting, the code completions, the IntelliSense, all that stuff is all available. Nothing's missing as such, right? And yeah, you can go look at the make target to see how that's working, etc. But that all works. So just keep in mind that for any non-cargo project where you're not using cargo as your build system, there's a way to do this. That's great. Secondly, the moment you do that, after you've done that, make sure you also start looking at macros. Because as I said, there's a bunch of macros in use over here. And you really need to know, I would recommend that is, how are these macros constructed? There's nothing different. You have procedural macros or macro rules macros, but how do I basically see what they produce is one big bone of contention, because that would clear things up quite a bit if you're looking at stuff. Anyway, so with those three things set, install Rust, get the working environment set up, and then ensure that you have Rust Analyzer, and ensure that you have a way to produce or to look at what a macro sort of produces. So that context should be sufficient for us to sort of start looking at the driver. Just give me one minute. I think somebody's calling me. Let me put myself on do not disturb. Okay, so with that context, let's just sort of look at what I've managed to eke out over here. So as I said, the PCI driver, the Nova Core piece is the low-level driver. It has what's called the driver interface. So if we go and look at something like, where was that, driver? If you go look at this, you'll see this, so one thing that you will see over here is, you will see that there's a probe method. This is a callback that the kernel will use when, after you've obviously registered your driver. So first you register your driver with the kernel, and when the kernel sees that there is a device that matches what you've registered as, I'm just going to call this probe method. And it's going to do things like enabling device memory, setting the bus master, all that stuff, and then it's going to do some mapping. So what do we mean by mapping? It's basically going to say some portion of the GPU memory that is used to sort of control the GPU. It's called a bar, etc. in the PCI world. That stuff is what you'd want to map in, and then you'd want to start working with it. But even before we get there and we talk about registration and all of that stuff, you'll start seeing this thing. You'll start seeing PinInit, and then you'll start seeing these macros, and that's why I said, it makes sense investing some time to understand how these macros are expanded. Don't bother trying, and I always say this, don't bother trying to go and look at the actual proc macro implementation for a macro and then read it through. It's just a little more, too much work. Better yet, you just need a way to expand these macros, and you look at what they produce at each call site, and then that should be sufficient for you to get started. So yeah, the first thing is, this is the driver, and over here you can see Nova Core is the low-level driver. An instance of that is called Nova Core. And you'll also see this proc macro, which is pin data. So with both of them in place, you're wondering, okay, what exactly is going on underneath all this macro magic stuff? That's something that I'll get to, but let's just to get through the other pieces. Then you've got GPU.rs. This is where you do things, the most basic thing. As I said, this driver is pretty minimal. You're going to be going ahead and doing things like chipset detection, architecture identification. So if you go into things like GPU.rs, you will see stuff, which particular chipset or which architecture are we talking about? Turing, Ampere, Ada, etc. That stuff. This is all basic stuff, and there's not much that you'd want to break your head over this for. What you would see is, again, you would see PinInit stuff, right? I'm going to get to that part just so that I just cover a couple of pieces. The registers that we have access to as part of the driver, that's something that is again in the regs. So it's a very simple implementation. There's a macro that says, here's the name of the register, here's the address or the offset, and then the bit fields and their description and what you can do with them and how you can access those bit fields. So yeah, there's sort of many ways to do this, and I believe the Nvidia team is using this method. I guess since it's simpler, it makes a lot of sense. Off chance, if you ever are looking at things like register, bit field, access, all of that, I would highly recommend looking at talk registers. It's really good. Type safety and a whole bunch of pieces are sort of added in there. Anyway, so that's registers. So the driver, the GPU hardware, some extra information about it, and the registers. Lastly, the firmware. So with Nvidia, what's changing is, previously, if you saw the previous diagram I showed you, let me go back there. I really need to sort of pin that to the top. So if you just look at the previous, so if you look at this diagram, you saw that, you've got the application, you've got the runtime, which is usually Vulkan and all the other stuff. You'd have a user mode driver, and then you'd have a kernel mode driver. In our case, I am not talking about the user mode driver at all at this point. I'm just talking about the kernel mode driver, which is two-tiered. All right. In here, when I say firmware, previously what used to happen is, I've sort of made notes of this, so let me just pull that up. But before that, previously what used to happen is the driver architecture was a little different. The kernel driver used to take on a lot of the load, like, basically constructing the right kind of command buffers for a given GPU, ensuring they're submitted, and the synchronization and the fencing and all of that stuff was, for the most part, handled by the core driver. That's part of the host that is in the kernel. With Nvidia, what's happening is they're moving to this thing called the GSP-based setup for the future. Okay, it basically means that you're going to move much of that complex logic out of the host driver into a firmware blob that's going to be running on an embedded CPU that's present in the GPU, which is, technically speaking, what you'd say what's called a command processor, the one that I've been talking about. Where is, this thing. It's called the command processor. So firmware that's running on the command processor is going to get a lot more responsibility in this GSP-based thing, right? Let me also talk about that a little bit more before I sort of lose that. So, here's sort of the difference. Traditionally, you used to have, like, the host driver has full visibility into all the GPU registers, the memory layout, command buffer formats, everything for a given GPU. The driver was particularly tuned for it. Now, with the GSP model, you don't actually do that. Like, for example, the Vulkan level abstraction will still go ahead and construct Vulkan command buffers and all of that stuff, but then you need to sort of map that to your specific GPU, etc. That's not being done apparently by the host driver. That's moved to the GSP's firmware. So this is what sort of happens. Typically, you'll just say, here's a job, here's a request I have. Take all the information that you've already put together as part of the Vulkan API. I'm just taking Vulkan as an example, and then pass that on to the GSP firmware. That's where it's going to do the actual construction of the command buffers for the specific GPU, etc. So that's kind of what I'm saying over here. The command buffer itself is user generated, but the host sort of does not parse it and then ensure that you're going to go ahead and provide the right kind of what you would say the right kind of for the specific GPU, you particularly produce the right kind of commands, etc. That's not happening at the host driver level now. It's actually happening at the firmware level. And these are sort of the commands that you're submitting: memory management commands, some context channel, all this stuff. So just the high level point to keep in mind is, even though user space generates these commands, it's not the job of the core host level driver, that's the kernel driver, to actually do the validation, the scheduling, the submission, none of that. it's just going to like proxy them to the firmware, and the firmware is going to sort of handle that. Right? So that's the small distinction that you would see in this new driver setup. That's the first thing. Okay. Let me just sort of. So that's the traditional host driver architecture versus the new GSP based drivers that Nvidia is tuning. Also, there's another reason why Nvidia wants to go down that direction, is because, you know, A, it's going to be easier to protect its IP. B, it's also going to be easier to update drivers and stuff and be a lot more stable. So it also sounds like you're going to be losing a little bit of control. That means you, the driver developer, etc. It sounds like that, but we'll see. I'm not that well versed, but I assume that will probably be the case. Okay, so we've looked at the core driver and we've looked at its sort of core components, and I talked about what the GSP differentiation is. So by the way, GSP stands for GPU system processor. It's nothing but a command processor. And it's where GPU runs part of the driver stack on internal firmware, and the host side driver becomes like a thin client. What gets offloaded, I've already sort of talked about it. So all that command building stuff, etc. Also things like power management, microcode loading, a bunch of things that, you know, this is the best part. This stuff you don't have to do in the host driver. And this can get really complicated pretty quickly. Okay, so the good and bad stuff about moving this stuff into a dedicated embedded processor inside the GPU. And then let's come to the nova-drm piece, all right? The nova-drm piece is kind of straightforward. The first thing that we do is, mostly what we're going to do is, we want to know that A, we have a driver that can pretty much handle the hardware that we want to be working with. So we need to somehow communicate that to user space as well. And that happens via the DRM. And then this macro sort of kicks in over here and sort of does this. I will expand the macro and sort of talk about how these macros are being used in some of the pin initialization infrastructure that's so important right now. We'll look at all those pieces. Anyway, so let me just go there straight off and look at that. So DRM, nova. Yeah, this is what I meant. In the core driver setup, you don't see a lot of drivers, but in the DRM space, you see pretty much every driver. So what's that? I'm not sure. Anyway, so if you see over here, the user API abstraction is something that is available to us over here. Then this is sort of where we're saying, okay, we're registering this as an auxiliary driver. That's sort of what happens over here. And if we went back to Nova Core, you'd also see that we're registering this as the core driver, right? So the two-tiered driver architecture over here. Wait, I don't want to see this now. The kernel is too big, man. You have to keep flipping around. Okay, we saw Nova Core. I'm just going to show you DRM as well. Again, let's just go through what's currently available, what kind of informations or what kind of implementations exists at this point. What is the state of it? So you've got, again, the driver, the file thing. I guess this isn't that important. This is mostly to do with how you would query ioctls and stuff like that. So that's all great. And then you've got GEM. I'm yet to sort of look at this very closely to understand exactly what is going on over here. But yeah, so that's the DRM portion of the driver. And the architecture we've already mentioned. This is sort of what I think it works like. Now, if somebody knows better, please let me know. We'll sort of go ahead and look at it. Sorry, I'll sort of go ahead and correct my understanding as well. But I think this is how it works. At least looking at that minimal implementation, I think this is how it works. So, the key components that I've noticed across all of them, this is the main driver. So this is a representation of a driver instance for the core driver, which is called Nova Core. And then you can have things like access to the GPU hardware abstraction through this as part of this. This is something that I've already talked about. Turing, Ampere, and Ada. Which kind of GPU are we talking about? What sort of capabilities does it have, etc. And the DRM data structures are these two, which again, this is an instance of the DRM driver. That's what this represents. AREF, the first time I looked at it, like, ooh, that's all cool stuff. What is this? You will see that AREF is nothing but the Linux kernel's version of ARC, or atomically referenced counter type. The only difference over here is you actually don't need to implement, or rather re-implement atomic reference counting because the kernel already has stuff like that. So how do you just tap into that? Well, you use a different type that says that. And then some ioctals. I'm not getting into that right now. But yes, so that's the two-tiered architecture. Great. We got that. We looked at the mental model, and we looked at the key components that make up those two different pieces of the driver. The way communication works with them, as I already said, is they sort of communicate the two different pieces, which is the what is that? The DRM portion versus the core driver. They sort of communicate with what's called an auxiliary bus. This is nothing fancy and all. I presume this is just some piece of memory that you're just talking about. It's not an actual bus. Okay, just so that you know. Otherwise, be stupid. Anyway, the reason I believe is this is because it provides a clean separation between actual hardware management versus a higher level of abstraction, that is DRM functionality. That's that. And then if I was to think about, a typical flow, given what is implemented, we'd say that the kernel goes ahead and does, actually, I have a better view of this. So let's go there. This one? Yeah. So I hope you can see this. This is, let's say the system boots up. Then obviously the kernel is going to do things like PCI enumeration, etc. It's going to find all the PCI devices that are attached to it. And the addresses for them are usually in this bus BDF format, which is bus device function format. At this point, when you register, your driver can be registered to say, okay, I handle vendor X, device Y. And then once this driver registration is done, the driver is going to go ahead and start, the kernel will try and match the driver to any device that it's seen. If it has seen one of them, then an automatic callback is called. You saw the probe method for your co-driver instance. That's sort of what's called. And in there, you do your initialization and all of that stuff. And then you can start accessing registers and blah, 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 and then you go forth. And that's pretty much that's what's implemented at this point. That's my understanding. This is the high-level flow of kind of the implementation that exists in the Linux kernel at this point. Now, with that context in place, without sort of, because there's nothing much to talk about over here as to exactly how things work, let's just look at one very specific thing, is how is the GPU driver utilizing the core Rust infrastructure that is already baked into the Linux kernel. So if we go ahead and look at the Rust repo that we already just saw, sorry, the Rust folder, you would see that there's a whole bunch of things in here. The first thing that you'd see is bindings. And this is what you need to wrap your head around, is a lot of the stuff in the Rust folder are bindings to existing C structures. That's how you would want to do it as well. You can actually go ahead and write your driver in pure Rust, etc. But if you want to take advantage of what the kernel offers, then that's all written in C. So you just want a binding to it. That's one. Then there's some helpers in here. Then the kernel stuff is where pretty much the bulk of whatever's on offer. If you're writing a block driver, or if you're writing a file system thing or whatever, there's stuff in here that you could make use of. That's what I understood. And then there's macros that you could sort of use. I haven't seen where it's used, but yeah, you can. And then the other piece that I've seen used extensively is pin initialization. And that's why it's called PinInit. So I'm not gonna like confuse anyone with what this is. So I've just made some notes over here. So effectively, what is this pin initialization infrastructure? So fundamentally in Linux kernel programming, you can have things like self-referential data structures. In other words, a data structure that probably has a pointer, and that pointer points to somewhere inside the data structure itself. So now imagine if you try to move that around in memory. You have a pointer that points to some actual piece of memory, and then you move that entire data structure. Then you've pretty much messed up or corrupted your data structure, right? So self-referential data structures, or even hardware-specific data structures that should be in memory at a specific location, is the requirement. How would you do that in Rust? In Rust, technically speaking, everything is unpin, in the sense all types by default will implement unpin. All right. Now you want to opt out of that. You want to specifically say, I want you to pin this particular piece of data to a certain spot in memory, a certain address is what I mean. How would we do that? That problem was already solved when Rust was dealing with async code, or rather async Rust, where the concept of self-referential data structures came in. The Linux kernel team have basically adopted the same thing and used it extensively to meet their needs. So that's what is being said over here. In kernel space, you often have structures that contain pointers to themselves or their fields that are tied to specific memory locations. They must never be moved once they're initialized, because that's the requirement. So this can get pretty complex. And the other thing is, let's say there's one of these pinned pieces of data that you want to deal with. And let's say you try to initialize something and it didn't work out. You really need to also be careful about that part. All right. So if you try to initialize something that is pinned, but it didn't work out, you need to like revert back, so that some other piece of code doesn't come in and think that, okay, this is sort of initialized, not initialized, this is in the right place, etc. So traditionally Rust doesn't offer this. That's what I said. Allows you to move values freely. Pretty much anybody would want you to do that, but in this case, that's what we don't want. So standard constructors cannot handle this. Partial initialization failures need careful cleanup. The pin stuff, where I will show you, this is where I mentioned, it's important to sort of start looking at, expanding those macros. So here's what I'm going to do because I think we've got a nice little flow over here. Without confusing anyone, I'll just explain one of these macros, and then you can apply the same pin initialization method to pretty much any macro, is the way I see it. So if we go back to drivers and go back to GPU, here And this is the first one. Let's say I'm looking at this particular driver, okay, which is part of the core driver. This thing handles the PCI interface, etc. So all this is great. You would normally see that there is a try pin initialize. And I hope you can see the comments over here. They're already there. This macro will try to construct, an in-place fallible pinned initializer for this struct, whatever the struct is. Okay, it's great. I mean, you can just look at it and say, okay, yeah, great. But then since I don't know anything about Linux, I'm like, what exactly is happening here? And this is where you can go ahead and make targets. So this thing, this .rsi that you're seeing over here, what are we saying? This .rsi stuff should actually have been named .expanded rs or whatever. So that's the expansion of this particular, great. So if I just go and look at it, let me go to the very top. You will see that for the driver module, all the proc macros are now expanded, and you'll be able to see exactly what's going on. And I'm just going to go through the pin initialization stuff so that, everything else can be sort of correlated if you're looking at other macros. And one more thing, this is not part of my tree, so you're going to see this not highlighted and stuff. So just bear with me on that. So here, the first thing that you see is if you look at driver, you've got Nova Core. This is pinned data, and then which one of the fields in Nova Core is actually pinned. So this data structure is actually pinned, and then in there, this field is actually pinned. This one's not. Okay. So sorry. So if that's what we're looking at, let me just close everything else. What was that thing? I forgot. Sometimes, I keep changing my shortcuts and I keep wondering how do I close all the tabs. Anyway, so if you go look at this again, you will see that Nova Core now is expanded. You don't have the pin data macro on it. But you do have this new thing that pops up over here, which is pinned data. And this is sort of what, carries through. We're going to say whenever you see the macro pinned data, well, basically what we're going to do is we're going to create a type. And that type is going to go ahead and you're going to implement a bunch of things for it. Primarily speaking, you're going to implement the initializer, or rather, you're going to find a way to initialize that particular field using an initializer. Okay, that's sort of what's going on over here. So this pinned data is going to be pinned to memory, and it's going to be initialized using an initializer that you provide. That's kind of what these two macros will ensure that gets done. And you'd also see the same thing. So you would also see that pin data implements clone and copy, great. But the implementation for pin data will also contain a method for each field. If you look at this field, it says GPU. So you're basically saying, I want you to initialize that particular field that for which you've marked this as pinned data, right? And I want you to give me a pinned initializer. That's all this boilerplate stuff is being set up for you. It's quite a bit of boilerplate. That's kind of what you will see in macro. That's why it's called macro magic. And nobody wants you to see what's underneath it. But some of the things that are interesting is some of this compiler-based trickery that's going on over here. How to make something. So one of the things that you want to ensure is, as I said, by default, all types implement unpin. So in order to avoid that, what you would say is, I'm going to create a struct called __unpin, and then I'm going to have a marker pin type for it, which will contain phantom data. And whenever the compiler sees this stuff, it's like, oh, okay, I don't think I can pin this stuff. Sorry, I can unpin this stuff. This is probably not unpinnable. That means it's not something that can be freely moved around, is what it's going to get a signature for. And when you sort of do this and include your type in there, you get all these pieces to say that the way I explain this is here, where we're looking at this particular field here. Yeah, here. And then this is sort of acting like a pinning marker. It's basically telling the compiler, do not auto implement unpin for this struct, because it is meant to participate in some pinning API. That is sort of that's the level of interesting trickery that's going on inside the macro implementation itself. So you'll see a lot of this stuff over here inside the macro implementation. And then finally, when we come down to the remaining portion, that is this implementation, you'll see that all this is great. You'll have a debug macro, that is not important. But then at this point, you will see try PinInit. Try initializing this struct using pinned initialization. If it fails, great, then clean up everything. That stuff is what you're going to see here. Where is that? Here. Right? You're going to see that here. And this is where you will start to see that, the pin data that we used, that we created on top, that's what this method is going to produce, which is pin data. And then we start using all of that type magic that we've infused it with to start initializing stuff. So our initializer is actually this, but this can fail. If it does fail, then we need to clean up and stuff. All that is sort of added over here along with the drop guards, etc. Right? So long story short, the pinning magic that goes on, or rather, where is that? This entire pinning infrastructure that's happening over here is, you can mark any data structure that you think should be pinned with this particular macro. And this is going to pin it in place to a particular location in memory. You can also specify, also be a little more granular and say pin these fields but not the other fields, or I don't care about the other fields kind of scenario. That's also something that you can mention over here. Underneath this, when this proc macro actually expands, what you would see is there's a lot of compiler, compile time sort of magic goes on to say how you would opt out of Rust's traditional behavior or conventional behavior of implementing unpin for pretty much every type, etc. All that stuff is taken care of, and then you are able to initialize that struct in place. And the other thing that is also sort of important over here is this is not a C type, but you might have structs that are already initialized, right? For example, I was talking to you about some aref thing. Those ones are already pinned, and you want to ensure that they remain pinned, right? So that's another place where these things also become important. So effectively, that's sort of what is going on over here with the pinning infrastructure. So the idea is pinned initialization. Objects are initialized in place and can never be moved once they're initialized. Field by field initialization is happening, where each field will have its own initializer. And then there's also failure handling. If initialization fails partway through, already initialized fields are properly cleaned up. And then all that type system magic that we use, will ensure, you avoid things like use after move or double initialization and all that stuff is avoided. So that's what I found pretty interesting in the whole Linux kernel thing. There's quite a bit of thought that's gone into how to leverage an existing, Rust. I wouldn't call it a feature. Actually, yeah, call it a feature, the pinning API, and use it to meet the needs that you have in the Linux kernel, right? So that's sort of the pinning infrastructure that's sort of built into the kernel, which is pretty great. Not great, but pretty interesting. So that's sort of what I wanted to cover. The other thing is some stuff about Bindgen, etc. I was just trying to understand how Bindgen's a little complicated over here because the build system is a little complicated over here. But at the end of the day, you can find all your... so if you're working with Rust, you can pretty much find most of your bindings in the commands or the build commands that you use in here, and the file that it uses to do the bindings, and then the actual bindings are somewhere present somewhere. Let me see if I can find it. Yep, they're here. So you got a massive file over here where all your bindings are present. These are, for example, this is the PCI device data structure. Okay, and here's where you see it's really good to have Rust Analyzer working because it's a massive data structure and you are accessing pieces of it from your driver, etc. So it makes a lot of sense to have it ready. Okay, so that's this. Oh wait, I want to do something else. Okay, is there anything else? And then you can actually go ahead and look at the internals of how pin initialization is implemented, but as I said, I wouldn't recommend it unless you're debugging something that really went wrong. It doesn't make sense. Yeah, so far I think a couple of things that are interesting to me, because I'm a Linux noob as well. I clearly qualify for that. Is it's not very different from a traditional large project where you're working with Rust. Like for example, you're working with a non-cargo build system. You're working with a lot of macro usage in many different places, and then you're using a bunch of different compiler trickery, etc., compile time trickery to get things done using those macros. Ultimately, this is the first time I felt like I can actually read code that's part of the compiler, right? Part of the Linux kernel. Keep saying compiler. Part of the Linux kernel, and didn't have to spend too much time. I just took maybe an hour or 2 hours to look at this code and say, okay, yeah, we can. This makes a lot of sense. This is interesting. This is how things are probably working. Of course, if I didn't get something right, please do drop a comment. That'd be really helpful. But I think Rust, I don't know if probably I'm biased as well, but using the strong type system of Rust, I was able to figure out, how different pieces sort of work for something that is very involved, I'd say, unless you're working with a GPU driver. I have no knowledge about how you build a GPU driver. Getting started was pretty quick. That's what I'm trying to say. Understanding things that are also a little bit in the weeds is also pretty easy. I think that's a pretty big boon for somebody who's, if I was to do this and see, I'd probably be like scratching my head as to, where is this? How does this work? Ooh, what's going on over here? Kind of thing. I didn't have to deal with that. right? You don't have to have prior knowledge is what I'm trying to say. You could probably just rely on your understanding of Rust and the type system to guide you through, right? So yeah, that's been interesting. And I really am looking forward to more of this, the way this driver is going to develop, and keep following along, and see if I can make more videos as I learn stuff and share it. All right, so I hope this is being useful. This is just some little piece that I wanted to just cover. It's not the cool, burn stuff for, compilers and static graphs and stuff like that. But this is very interesting because at the end of the day, no matter what you do, you'll end up here. You need to figure out what's your driver doing, how is it doing stuff, etc. And you probably want to know how it's doing stuff. All right, so that's about what I wanted to talk about, at least for today. As always, I will leave these notes in a gist on GitHub. Please feel free to use them if you think they're useful. All right, that's about it. Thank you. Have a good day.